Hello, everyone.
Всем добрый день.
So we have been hearing about complex AI models, GPT-3.
Обсуждали сложные
What
и
worries me
модели
is the
GPT-3.
cost associated with training such
Моя озабоченность — это
astronomical models.
стоимость,
And
затраты,
it's not
которые
just
нужны для
the
таких астрономических моделей.
energy efficiency or the money associated with training those models. What worries me is that there are very few entities that can play and train such models, and the whole world is expecting that they will use the models trained by very few companies. And as we know, that AI is susceptible to manipulations, and it's almost impossible to figure that out. Fortunately, I'm here to not talk about the problem, but a solution, which is the research that I have been doing for the past 7 years. I'm going to talk about an algorithm which I think is scalable and sustainable, and it can train billions of parameter models on a hardware that almost everyone has, the CPUs. Before we get into the algorithm, let's quickly take an overview of the modern AI landscape. We need large models. It's very clear to us the model sizes are growing. There was a paper in 2017 by Google which was aiming to train about 137 billion parameter for a data set that has about 100 billion words. And in the abstract of the paper, there was a statement that said, model capacity is critical for absorbing the vast quantity of knowledge in the training data set. In the same paper, they claimed that they have a 10 times bigger data set, a trillion word corpus, and they plan to train a trillion word parameter model for that corpus. And the message is very clear. As the data set grow in complexity, the model needs to grow. And this can also be explained easily using the concept of information theory or the capacity of the model, in which if we are becoming ambitious with our machine learning models, as in we are aiming for a model that trains and assimilates the information and all the variations in the data, the model cannot be small. The capacity of the model must be such that it can assimilate all the variations in the data set. And that is what we are observing even with our AI models. The models are getting bigger and bigger as we try to improve the accuracies on our data sets. There's another interesting thing that is happening. The models are getting bigger, but they're also getting simplified. So we all have heard about very complex sort of models, CNNs, RNNs, LSTMs. It turns out, starting last year and a few years back, there was this popular paper, Attention is All You Need, and that claimed that you can replace most of the RNNs and LSTMs by a simple embedding kind of model with attention mechanism. Starting last year, people have started questioning whether we need convolutions. And in fact, there are papers in which you can treat image patches as words and pretty much do something like an embedding model and get the same accuracy as some of the sophisticated convolution neural networks. With one of our major oil companies, even we were able to demonstrate that for some of the most complex seismic inversion tasks, we don't need convolutions. We can work with something which is very simple, something closer to an embedding models or even fully connected models. Even the popular attention mechanism is now in question about whether we really need them. Attention can be replaced by something which is much simpler, calling it synthesizer. Even I have worked on a model called Pair Connect, which is more or less a multi-layer perceptron and is even more powerful than attention. And the most sophisticated models that we know of, like Facebook's DLRM, DSSM, these recommendation models, are actually fully connected networks. So models are getting bigger and they are getting simpler. And so what matters is actually the training time. So if we look around and ask the question, how does a company transforms AI into production, it amounts to a sequence of trial and error. We start with a problem, we hypothesize a model, we train and validate it, then we hypothesize a better model, and the process continues. And in this case, the slowest process is the training and realizing the validity of the model. Even efficient inference is about searching the cheap model with good accuracy. As a result, everything boils down to the training time and cost associated with it. If we can move the training time, if we can move the training process faster and reduce the training time, that directly translates into AI innovation. And it is not surprising if we look around who is producing some of the best models out there. Well, the entity which has the most extensive computing resources, the entity that has the capability to validate these larger models faster than others is naturally making faster progress. No wonder specialized hardwares are getting more and more popular, because these hardware promises faster training. They have specialized architectures meant for training large neural network with a lot of dense tensor operations. They can utilize a lot of parallel cores for a very specific kind of operations in which the memory access pattern is regular. And of course, this becomes very appealing for neural networks, because currently the way neural networks are trained, they use a sequence of matrix multiplications. So where are we at? We are at a junction where we are training larger and larger models. The data is growing bigger and bigger. In fact, according to OpenAI, the compute power required to advance AI is doubling every 3.5 months. That's exponential. However, our algorithms are the same that we used to train neural networks back in the 80s. It's still backpropagation or a sequence of matrix multiplication. And parallelism is giving us an improvement, but only a constant factor. And the procedure is not sustainable. So in this chart, I'm showing the carbon footprint of different things, which includes a round-trip flight, a human life, an American life, a US car in its full lifetime. So imagine a car, you buy a car and run it for its own lifetime. That's about 126,000 lbs of CO2. However, training a transformer model from scratch with a neural architecture search is 5 times worse than that. Clearly, this is not a sustainable solution. What puzzles me is that we are thinking of moving to specialized computing hardware and chips, which are about 3x more costly. We are ready to throw away decades of expertise in commodity pipelines. We are ready to work with hardwares that are hard to virtualize, and there are burdens related to their low main memory. We have to work with distributed computing if we are looking at much bigger models. And obviously, the energy numbers are off the charts. But we are not thinking about an alternative to the good old backpropagation algorithm, which we all know is inefficient. And I think there is a reason for it. The reason is that backpropagation is really a simple algorithm. It's a bunch of matrix multiplication. And we have gotten used to it. I mean, there are so many good implementation out there which accelerates matrix multiplication and makes backpropagation easy to use, that we cannot think a world without these packages. And I think that is what is stopping us to rethink some of these algorithms. So when we start thinking about smart and efficient algorithms for training neural networks, we can take inspiration from the brain. We all know that brain is significantly more efficient than any neural network that we train. And one of the reasons for the efficiency of brain is known as sparse coding. So imagine I am seeing a pattern of a cat, and in the neural network jargon, the cat, you can compute the activation of cat on all the neurons. Some neurons will have large activation, some will have small. And that is how we currently train neural networks. But we know that there are certain spike neurons in our brain in which a pattern only activates very few spike neurons, as shown on the right-hand side, which is also popularly known as sparse coding. The thing to note here is that the way we train our neural networks, even though a neuron will have a very large activation or a very small activation, we spend equal amount of energy or computation for that neuron. We just compute its activation. The arithmetic is the same. Whereas brain does not spend a lot of energy on neurons that are not relevant. And this is something what I am going to show we can achieve through smart algorithms. Before we go there, there's a fact we all know and agree is that backpropagation is not some of the most efficient algorithm out there. In fact, it's a lot wasteful. A very easy way to see this is imagine a neural network. Let's look at this 3-layer neural network and a pattern of cat. Let's assume that the hidden layer has ReLU activation. Now, ReLU activation throws away all the activation that are less than 0. So from a computational perspective, I take the input pattern, compute the activation of all the neurons, and then I throw away all the neurons that has activations less than 0, which is kind of wasteful. So I'm throwing away 50% of the computations. In fact, there is literature around adaptive dropouts and winner-take-all strategies which tries to mimic sparse coding, but in a way that says that, well, we could actually ignore 90% or more of the neurons by only picking neurons that has large activation. But computationally, that's a nightmare because we still compute all the activations and then throw away 90% of the activations that we all computed. So it's not a very energy efficient solution. Now the sparse coding is still there because we are throwing away a lot of neurons, but we are not utilizing the efficiency, as in we are still computing all the activation. So the question that I have been thinking about for the past few years is, can we avoid computing most non-relevant activation? So essentially, if I have 1,000,000 neurons, and if I look at an image of a cat and only 100 neurons are relevant, can I only spend arithmetic, which is, let's say, proportional to 100 instead of being proportional to 1,000,000? Can we do that? Obviously, that sounds a little absurd. Well, I don't know what pattern is. If I see a cat, it's going to be a different set of neurons. If I see something else, it's going to be a different set of neurons. How do I know which neurons will fire without even computing those activations? Well, it's almost right if we are thinking in terms of exact arithmetic. But we solve this problem almost every second in the form of information retrieval or web search. So when we fire a query at Google about, let's say, artificial intelligence journey conference, the Google does not go and scan all the trillion web pages out there and compare it with the query. It finds the relevance of the query with the web page automatically because it has indexed or reorganized the web into certain data structures. And we are solving more or less a similar problem here, that we have a pattern like a cat, and we are asking a question, what are the relevant neurons? It's a search problem. So just like we can index the web pages, we can index neurons, and that is what we are going to do. We are going to organize neurons in our neural network into memory locations, and we are going to query the pattern for active neurons just like we query the web. So this is the, what the framework looks like, which I'm calling deep learning plus associative memories. This is what we have built. So the way it works is, we initialize a neural network, and every neuron is the entity that we want to reindex. So we initialize the neural network and we reinitialize the indexes of the neuron. In this case, I'm illustrating them with a bunch of hash tables. So every layer has a whole bunch of hash tables, just like any information retrieval system has. Now, when I have an input, the input queries the hash tables for the relevant neuron, just like the web search queries a query for the the relevant web pages. In this case, let's say I land up in bucket 3, and I'm only going to consider neurons 1, 2, and 5. After that, I only compute activations of the neuron that are relevant right now to the query. Now, I have a sparse vector in which I have spent computations for 1, 2, and 5, and I have not even touched anything to neurons 3 and 4. I get a sparse vector, and then I query again to the next layer. Things to note here is that I am getting the sparsity pattern of the neural network just by a hash query and few memory lookups. This way, if there are 100 neurons that are relevant to the input, then I am only doing work of the order of 100, very similar to sparse coding. So once I have an input, I get the sparse pattern from the neural network. I only feed forward on those neurons and backpropagate and only update the relevant parameter and then reorganize them into the hash table. Effectively, this way, I am only doing computations that are of the order of active neurons rather than everything out there. So if I have 1 million neurons and I look at an image of a cat, I am only doing arithmetic of the order of 100. And I want to argue that this kind of achieves that brain-like efficiency, that I am not spending any arithmetic or any memory fetch or any energy on the neurons that are not relevant to the training process. And this way, we can achieve sparse coding in a very efficient way. Unlike what has been tried before, where we first compute most of the activation and throw away most of the neurons. There is one added bonus here, which I think is worth highlighting, that is data parallel training. So imagine I'm looking at 2 patterns, and both the patterns activate roughly disjoint set of neurons. In that case, I can update them in parallel. I can learn about a cat and an image of a bear simultaneously. It should be noted that gradient descent otherwise is inherently sequential. I need to first update my belief about cat to make a prediction on a bear. But if I am doing it in a sparse coding way, there is a hope that I can train them in parallel. So well, I have made it sound simple, but this is the system that I have been building for like past 3 years, and there has been about 10 to 15 papers gone into how to make it work. But we have an implementation, and we want to see how good this method is compared with other accelerators. So we took a Kaggle Amazon 670 product recommendation task, and we created 2 benchmark networks, one with 200 million parameters and the larger one with 1.6 billion parameters, and I ran 3 competitions. One is we use the optimized version of TensorFlow, which is by Intel MKL DNN, on a CPU. Then we use the TensorFlow implementation on GPU, the A100, the most popular GPU out there. And then we have, through Third AI, an implementation of the algorithm that we just saw, the BOLT software, which is implemented in C++ and parallelized over OpenMP. And these are the 3 softwares that we are going to compare. Sorry, one of them is also a software on an A100 GPU. So these are the 3 accelerators that we are going to compare. One is the existing software accelerators on CPU, one the software accelerator for the best GPU available, and third, the algorithm that I just showed you implemented optimally. And we are going to look on 2 benchmarks, a small one with 200 million parameter models and a large one with 1.6 billion parameter model. And instead of looking at any other metric, I will look at a metric that matters the most: accuracy climb with training time. Here are some of the results, what it looks like. On the left, you are looking at the time it takes for different competitors to complete one epoch. The orange bars are TensorFlow on 3 different CPUs. I'm showing you AMD, Intel, and ARM CPUs. And the orange bar is the TensorFlow's implementation on those CPUs. The blue one is the BOLT's by third AI, which is the algorithm that I just showed you. And for reference, I have also showed the same model when it ran with TensorFlow on a GPU. On the right, you will see on the x-axis, there is the wall clock time, and on the y-axis, there is the precision at 1, the metric for recommendation, as in the accuracy climb with the running time. We can clearly see that with the right algorithm, any CPUs can be more potent or as potent or even more than powerful 800 GPUs. In fact, if you look at the time to reach any particular accuracy, this algorithm beats the heck out of anybody else, which is quite exciting. Now let's go even further and look at a 1.6 billion parameter model. Oh, wait a sec. Before that, there is Apple M1 laptop here. So imagine training 200 billion parameter model on a laptop, which is almost as fast as an 800 GPU. And again, these are dense, fully connected neural network, a workload which is considered ideal for GPUs. Let's look at a billion parameter model benchmark. So here I'm training a 1.6 billion parameter model. And by the way, I cannot train them on 1 or even 2 800 GPUs. I need 4 800 GPUs because GPUs have limited memory, only 40 gigs in this case. Whereas with if I just use TensorFlow CPU, the numbers are pretty bad because, well, CPUs are not that good if you are doing dense operation. But if you are using the smart algorithm, then third AI's implementation takes about 1300 seconds per epoch compared to 1600 seconds with 4 NVIDIA V800 GPUs. Now, we have been talking about the sparsity and an associative memory to achieve that sparsity. If we use naive way of implementing sparsity, which is already there in the TensorFlow package in the form of sampled softmax and other things, it hurts the convergence. You need to find the relevant neurons given to the pattern. If you don't find relevant neurons, it's going to hurt your accuracy. Right now, what I showed you, so this plot was actually with a refurbished V3 Intel CPU. And even this one was a refurbished V3 CPU. If we use modern CPUs like Copper Lake and with a lot of cores, then we can be at about 15x faster than V100. These are benchmarks, and this is a joint collaboration with Intel where we showed 3-4 different data sets from recommendations to NLP and how we can accelerate algorithms on CPU, some of the modern CPUs leveraging AVX and bfloat 16 to get some very impressive speed up over GPUs. When we implement this, we are now, even through third AI, we are exposing these capabilities in Python. So if you ask a question, how can I invoke this engine in my workload? Well, it's probably 1 or 2 line change. So you define the model the way you like in TensorFlow, Keras, and you can do is a simple switch the engine to this algorithm to get all the acceleration on any platform that you like, which we call the Bolt package. So here is what I'm putting the two alternatives in perspective. On the one end, we have Bolt, which compute hashes of a data. There is hash lookup and aggregation. We are talking about decades of work in databases that deals with hash tables. It leads to a very efficient algorithm with few arithmetic. It is low in latency, uses simple hash table, but there is unpredictable memory access, as in access is randomized. That is when we cannot directly leverage these hardware accelerators. On the other hand, we have the algorithm of the 80s backpropagation, which is matrix multiplication. There is a lot of hardware support, but it cannot scale when your network size grows very large, and obviously it's expensive and the energy numbers are off the chart. What excites me is that if I can make AI training available on CPU, it can change the complete economics of how we view deep learning. CPUs are so available. Lots of them are sitting idle. Most hardware acceleration are vendor optimized and proprietary, and it's not easy to deal with them. CPUs are architecturally consistent, cheapest, and fully virtualizable. And by the way, if I can enable AI training on cheap refurbished CPUs, I can as well train and not just inference, train an AI model on IoT IoT devices, because most of the IoT devices like Raspberry Pis are CPUs with few cores. And I think this is going to be very exciting, the possibility of training and or fine-tuning AI models on IoT devices. Currently, it is assumed that training is a cloud job and inference is possible on the edge. But I think that can change. I will conclude with the fact that we are still using the same algorithm designed in the 80s. All the implementation has only one hammer, which is matrix multiplication. Unfortunately, the matrix sizes has grown beyond limits. It's time we move beyond that, and I'm glad to report that we already have demonstrated success with BOLT and new algorithms, which I think is a way for future. And, well, people are agreeing that sparsity is the next big deal, but making it work will require efforts from several places, and I'm glad that I have demonstrated you one of that. With that, I will end with the set of references that I'm talking about. Thank you for listening.
Thank you very much. Thank you for being here offline. Your technology is really a breakthrough. So we'll be glad to see you here next year too. Thank you very much indeed. Thank you.